Okay, guys, this is the second part of section 7.2, trigonometric integrals. And in this part, we are going to talk about tangent and secant integrals. Before we start doing actually tangent secant integrals, let me remind you like basic formulas for tangent and secant. So first, secant of x is what? It's 1 over cosine of x, right? Second formula we'll need derivative of tangent of x, if you guys remember from calculus 5a, is equal to secant square of x. You can just differentiate tangent actually. Tangent represented as sine over cosine, and then differentiate sine, multiply by cosine using quotient rule, and then differentiate cosine by sine. You are going to get actually 1 over cosine square, which is secant square. And the last important thing, or maybe we should differentiate also secant, because derivative of secant is not very obvious, and I kind of don't think that you know it. So let's differentiate secant of x derivative. And in our case, because secant is 1 over cosine, we just need to differentiate cosine to the power of negative 1 over x. This is not inverse, that's 1 over cos, right? When we differentiate 1 over cosine, we are going to get minus 1, right? Because of this minus 1. And then cosine to the power of negative 2, minus 1 unit, right? And then derivative of cosine. Argument here is a cosine. We need to differentiate cosine. It's going to give us sine of x. And was minus, right? Derivative of cosine is minus sine. So this minus is going to disappear. If I rewrite it as a fraction, I'm going to get a sine of x divided over cosine square of x. We know that 1 over cosine is secant. So we have sine of x by 1 over cosine of x by 1 over cosine of x. So actually this one is secant and this one is secant. And we are going to have oh, I think we can actually have this as a tangent. The only one secant is good. So this one is tangent. So let's use tangent of x by secant of x. Yeah, you can write it down as sine of x by secant square, but for our purposes, it's better to represent as tangent and secant. So we don't need a second secant. This one is not necessary. Okay, so that's a derivative of secant. Interesting, right? Derivative of secant is not just secant, but secant tangent. Last fact that we need today is a Pythagorean identity for secant tangent. I did this identity already once somewhere like, I think maybe section 2 or 3 when we were doing trigonometry, but I'm going to do it one more time. So Pythagorean identity for sine and cosine is cosine square of x plus sine square of x equals 1, right? If we divide this identity by cosine square each term, what are we going to have here? We are going to have 1, right? Cosine, cosine. Here, sine over cosine is tangent, and square is going to give me tangent square. And this side is going to be equal secant square of x, right? It's 1 over cosine, because it's squared, it's going to be secant square of x. This is a fourth fact that we'll need to use today. So fact number 1, fact number 2, fact number 3, and fact number 4. Fact number 3 is actually the final answer is over here. Okay, so let's kind of see how all this is going to help us to calculate integrals. I'm going to start with something simple, and I'm going to start numeration of examples from 1 again, just because I don't remember what was the last example. So let's try to calculate the integral of tangent to the power of 6 of x multiplied by secant to the power of 4 of x dx. So guys, what I'm going to do, I'll need to do substitution here. And when you deal with tangent secant integral, substitution is either tangent or secant. Which one to choose? Well, guys, for example, we use substitution tangent. Then tangent is going to become just a new variable. From secant, we'll need to use 2 seconds to make du, right? Tangent derivative, if we use it as a substitution, supposed to have also secant squared dx. There's going to be 2 seconds left, which we can convert using Pythagorean identity into expression in tangent. So it's good substitution. And for now, you guys believe me that it's a good substitution, and then you are going to understand it yourself eventually after several examples. So u equals tangent, du equals secant square of x dx. Secant square, the derivative, dx, right? So what I have u to the power of 6 instead of tangent to the power of 6. Secant to the power of 4 is going to give me, like, I'm going to write it down, secant square and secant square dx. This one is going to turn into du right away, already know. And this one, using Pythagorean identity, is going to turn secant square over here, going to turn in 1 minus u square. Tangent square is kind of going to u square. Going to have pretty simple expression, u to the power of 6, 1 minus u square du. Also polynomial, it's easy to integrate. So I'm going to continue over here. So I have integral u to the power of 6 minus u to the power of 8 du, which is going to give me u to the power of 7 over 7 minus u to the power of 9 over 9. And if I go back to my original tangent variable, I'm going to have tangent of x to the power of 7 over 7 minus tangent of x to the power of 9 over 9 plus a constant. So not difficult, right? Well, that was a case when you have even power of secant. Why even power of secant is important? Well, if you choose substitution tangent, it does not matter what is the power of tangent here. Odd or even, it's going to become a new variable automatically. But for secant, everything is not that simple. Your power here must be even power because you are going to take 2 seconds for derivative to make du, and the leftover seconds, if you want to convert them into tangent, supposed to be square or fourth power or any other even power, because we can convert it to tangent without getting a square root, only even powers of secant. So I'm going to label this. This one's supposed to be even, and this can be anything. Well, I need to remember, that's it. Odd or even, doesn't matter. Okay? Okay, let's move to example number 2. One, we know that in case of even power. Now, let's consider example number 2. Tangent to the power of 5 of x, secant to the power of 7 of x. It's kind of high powers. So here, guys, we check the power of secant. It's not even. So kind of not good. It's not secant. The substitution of tangent is not going to work. Let's try different substitution. Let's try substitution of secant. What is going to be du in this case? Well, we remember the derivative of secant, and I differentiated it somewhere. It's tangent secant. So I'm going to write down tangent of x, secant of x, dx. Now, guys, let's first kind of combine everything here to get like what we have. So we'll need tangent and secant to make up du. So I'm going to take one tangent and one secant to make up du. If I do this, I'm going to have tangent to the power of 4 of x, secant to the power of 6 of x, and here going to be tangent of x, secant of x, dx. So this is going to become my new du, right? Secant is going to be converted into the new variable by itself, and it does not matter what is the power of secant. Tangent is going to be converted into secant using Pythagorean identity. Just we'll need to kind of remove like move this one to the right side, right? So I'm going to have secant square minus 1 here, and that's going to be tangent square, but because it's squared, we're moving one more square. Okay, so let's look at the final expression. U square minus 1 squared, u to the power of 6, and du. Everything converted. But guys, if the tangent was not even here after you took 1, it would not work. For secant, we don't care about the power. But for tangent, we'll need all the power. Why? Because to make a derivative of secant, we're going to borrow one tangent from here. And the result must be even after to convert it into secant. Okay, so we are going to remember about this. Well, let's finish this integral quickly. So again, we'll need to open the square, not difficult. U square squared u to the power of 4 minus 2u square minus 1 u to the power of 6 du, and multiplying or distributing u to the power of 6, we get u to the power of 10 minus 2u to the power of 8 minus, I think supposed to be plus, a mistake, u to the power of 6 du. That's integrated. So we have u to the power of 11 over 11 minus 2u to the power of 9 over 9 and plus u to the power of 7 over 7. Going back to original variable, we are going to have secant to the power of 11 over 11 minus 2 over 9 secant to the power of 9 and plus secant to the power of 7 over 7 plus constant. So let me go back. So the power of tangent must be odd. So my first case, the power of secant is even, power of tangent, second case is odd. Now guys, there are some cases which don't fit into these two cases. For sine and cosine, we always have a case, either like both power, one power is even, another power is even, or like both powers are odd, one is even, another is even. And like two even powers will be converted into a reduction formula. For tangent and secant, unfortunately, we don't have a formula or substitution which covers all cases. Because if secant is odd, then formula is not going to work. And the tangent is even, if you combine this, odd secant with even tangent, none of this is going to work. What should we do in this case? These cases must be solved separately. And I'm going to solve some of these cases separately. But before we go to these special cases, we are going to consider some self-problems. So let's label them at 1. And I want to kind of create many problems of similar type. Let's do something like, okay, this problem is probably too easy. The second problem. Okay, so two problems. And we're going to move to special cases, which are not covered by secant tangent substitutions. We learn. I'm going to label them special cases. Remember, when special cases happen, well, when the power of secant is odd and the power of tangent is even. We're going to start with special case number 1, and that's going to be integral of just secant of x. dx. You probably ask me, oh, what? There's no tangent at all, right, guys? The power of tangent is zero. We are going to treat zero as even power, but secant is odd. And what should we do in this case? Unfortunately, guys, uh, the substitution which we are going to use is very, very artificial. But if you see it once, you probably are going to just remember how it works. So I'm going to use very super artificial substitution, which is going to be sum of secant of x plus tangent of x. Looks crazy because your integral doesn't have this sum, and nothing tells you that we can use substitution like this. But you are going to see how it works. So what is going to be du in this case? First, derivative of secant is secant tangent, right? Derivative of tangent is secant square of x. And if I take secant of x outside, I'm going to have tangent of x plus secant of x. Well, it still doesn't tell us much. I'm sorry, I'm supposed to write down dx over here. Now I'm ready, after this special work, I'm ready to do the integral, guys. What I'm going to do here, special trick again. I'm going to multiply this expression by secant of x plus tangent of x. And I'm going to divide it by secant of x plus tangent of x. If I do this, I'm kind of multiplying my fraction by 1. No change. The fraction happens. Now, how it's going to help me? Look at denominator. Denominator is basically my u, right? Look at numerator. Secant plus tangent. Secant plus tangent dx. Numerator is my du. Now you see probably why I did this substitution. So we have du over u, which is going to tell us that the result is going to be just a ln of absolute value of u, right? If we go back to original variable, which is secant plus tangent, that's going to be a ln of secant of x plus tangent of x plus a constant. And that's going to be the integral of secant. Remember, we have like integrals of sine, cosine, and we even learned how to do a ln in the substitution integration by parts section. Well, now we know how to integrate secant. Each function is going to have something. Secant is actually going to be a ln of secant plus tangent. My suggestion is to memorize this formula because usually, well, this special substitution never comes into hand unless you kind of have very, very good memory. Very good. So that's my special case number 1, when secant power is 1 odd and that there is no tangent. Let's imagine that the power of tangent is 0, which is going to be considered even. Now, guys, let's consider next integral, and that's going to be secant cube, which is also going to give us odd power of secant and no tangent. Okay, how are we going to deal with secant cube? Secant cube, we're going to play a little bit. Going to represent that secant cube as a secant of x by secant square of x dx, which is going to give us secant of x multiplied by d tangent of x. Derivative of tangent is secant square, so that's going to be our. I'm going to use by parts integration. So this is my function f, and this is my function g. So secant of x multiplied by tangent of x minus. Remember that now I have to copy my function g, which is tangent of x, and differentiate my function f, which is secant. And derivative of secant is secant tangent. I'm going to move to next line and simplify a little bit my expression and make it. I want to keep it one. And otherwise, also I want to simplify it. So, sorry, no equals sign. First, I'll need to copy actually. So I have secant of x multiplied by tangent of x minus, and here I have tangent, secant, tangent. That's tangent square, right? Tangent square using Pythagorean identity. We scroll up, where is it? Tangent square using Pythagorean identity is equal secant minus 1. Secant square minus 1. It's already know. Secant square minus 1 multiplied by secant of x dx. And one more time, and you guys are going to see where I go. Tangent of x minus. If I open parentheses, I'm going to have secant square and one more secant cube dx, right? I'm splitting one integral into two. Minus is going to give me plus integral of secant of x dx. Now, guys, you probably are going to see that my original integral is going to be equal to this expression plus original integral and plus some integral which we just know how to calculate that we just calculated. So what I'm going to do, guys, I'm going to move this one, original, together with this. And because this has minus, this has plus, it's going to double it. So I'm going to have two integrals of secant cube of x dx. And on this side, I have secant of x, tangent of x, a product, right? Plus this integral of secant, I do know it's ln absolute value of secant plus tangent. Secant of x plus tangent of x, right? Now the only step I'll need to do is to divide by 2. Everything. So I divide by 2 here, I divide by 2 here, and I divide by 2 here. Well, here 2's are going to cancel, and that's the integral I'm searching for. Just don't forget the constant, that's the answer. So integral of secant cube equals secant tangent divided over 2 plus 1/2 of ln secant plus tangent. Now, guys, for self-work, I want you to do problem number 3. Now, integrate this one. Secant of x, odd power of secant, by tangent square of x. Actually, we kind of did this integral already somewhere. Well, just do it and see how you can kind of apply knowledge we learned. Okay, that's all. And I think that this you can kind of do more problems in the homework, but otherwise that's all for now. I'm going to do more integrals maybe in the next video.